Hi there everyone, welcome to another video covering OCR Further Maths. Today we'll be covering question 9 from the 2019 Pure Core 2 paper. And as you can see from the question and the diagram, this question is about polar curves, which is a very common topic in the OCR Further Maths, OCRA papers. And it comes up basically every year, so it's very important that you're confident with both the standard questions but also the more difficult style of questions in terms of polar curves. So let's head straight into the question. So it says you must show detailed reasoning, which means you show all of your working in order to get the marks. And it says the diagram below shows the curve r equals the root of sine theta times by e to the power of a third cos theta for theta is between values of 0 and pi inclusive. And then it shows us this diagram, and all we have to really observe from this diagram is that it's a closed loop, which means it has a defined area. And as you can see, it starts at theta is equal to 0 and then ends at theta is equal to pi, so it's gone through pi radians or 180 degrees anti-clockwise. So that's kind of what you have to understand from this diagram. Not too much else is really that important. And part A says that find the exact area enclosed by the curve. Now, finding the area of a polar curve is a very, very standard question. So everyone should basically, towards the end of the course, you should all basically memorize this formula, but it is given in the formula book just in case, and that's the area is equal to half the integral between b and a of r squared d theta, and r is the formula for the polar curve, b and a are the boundary conditions, so all we have to really find out from to be able to answer this question is what are the boundary conditions, and for us in this loop it's pi and 0. So that's what we're going to do right now. We're just going to plug r and the boundary conditions into this integral and solve this integral. So it's a half between pi and 0 of r squared. So that will be root sine theta e to the third cos theta squared d theta. And then we just have to expand and solve. So that gives us half the integral between pi and 0. So sine to the root sine theta times to the power of 2 is just sine theta, and e to the third cos theta to the power of 2 is just e to the 2/3 cos theta, and that we integrate this with respect to theta. So that's pretty simple expansion. And now to solve this integral, there are a couple of ways you could do it. So the less common ways I'd say are probably u sub, and maybe you could do this by parts as well. But I think the quickest way, and if you've done a lot of integration at A level and also in further maths, you should be able to spot this quite quickly, and that's reverse chain rule. So I'm going to use reverse chain rule to integrate this expression here. So all I have to do is kind of rearrange this line here so that e to the 2/3 cos theta differentiates into something with a sine theta, because we know cos theta differentiates to minus sine theta, so 2/3 cos theta differentiates to minus 2/3 sine theta. So all we have to do is just do half the integral between pi and 0, and we have to get 1 from minus 2/3. So if we have negative 2/3 times by negative 3/2, that will give us positive 1, as we want, sine theta, e to the 2/3 cos theta with respect to theta. And all we have to kind of do is just take this negative 3/2 and take it outside of the integral. So that will give us negative 3/4, the integral between pi and 0 of negative 2/3 sine theta, e to the 2/3 cos theta with respect to theta. Now we just do some simple integration, and that gives us negative 3/4 and square brackets e to the 2/3 cos theta between pi and 0. Now we just plug in pi and 0 into this expression here, so we get negative 3/4, and cos of pi is just negative 1, so that gives us e to the negative 2/3, and then negative negative is positive, so we have plus 3/4 e to the, and cos of 0 is positive 1, so we just have e to the 2/3, and we can just rearrange this to make it a bit nicer. 3/4 e to the 2/3 take away e to the negative 2/3, and that is our final answer. So that's a pretty simple question, worth 4 marks, and then now we'll move on to part B, which is slightly more tricky and worth slightly more marks. So for part B, it says show the greatest value of r on the curve, which we've been given is this. It's very long to read out, but it's root of root 3 over 2 times by e to the 1/6. So basically what we're going to have to do here is apply some different topics to polar curves that we probably haven't covered in as much detail, but it's nothing to be kind of too frightened just because it's 7 marks. So the first thing to notice is it says the greatest value of r. Now if you ever have a curve in regular A-level maths and it says find the greatest value or something like that, usually what you're trying to do is maximize in some way, either maximization or trying to find the stationary points or something like that. So what we're going to have to do here is maximize the value of r on this curve, and then we can find the maximum value of it. So the way to find the maximum value of something, either maximum or minimum, is by differentiating and then making it equal to 0, making the differential equal to 0. So that's what we're going to do here. I've already written out the formula for polar curve out, so it's a bit easier. I don't have to go up and down so much. But r is equal to root sine theta times e to the 3rd cos theta. Now we have to differentiate this with respect to theta. So what we're going to do here is use the product rule, because we have kind of 2 functions. We'll also have to do the chain rule a bit because we have e to the 3rd cos theta and root sine theta. So the root sine theta we might have to do a bit of chain rule with, but nothing too difficult, nothing that you haven't seen in A-level maths. So if I call this function u and I call this function v, we know that the product rule is v u dash plus u v dash, and then all we have to do is write on this side u dash is equal to 1/2 sine theta in brackets all to the negative 1/2 times by the differential of sine theta, which is just cos theta, and then v dash is equal to negative 1/3 sine theta, because cos theta differentiates to negative sine theta, times by e to the 1/3 cos theta. So a bit of chain rule here, and now we're going to put this into this formula here and use the product rule. So v is e to the 1/3 cos theta, and then we're timesing that by u dash, which is something like this, 1/2 sine theta to the power of negative 1/2 cos theta, and then the next one plus is u v dash. So u is sine theta all to the power of 1/2 times by v dash, which is just negative 1/3 sine theta e to the 3rd cos theta. So now all we have to do is make this equal to 0, as I've done here, because we're trying to maximize it, and we have to in some way solve it to find a value of theta, then we can plug that into the original formula and get this answer here. So what we're going to do is we're going to try to factor out some things, just like you would with any expression when you're trying to solve it. And the first thing I can see is that both terms have a common e to the 1/3 cos theta. Now, what you should know from solving many questions before is that e to the power of anything never equals 0. So first I'm going to rewrite this, and then I'll show what I mean. And it's take away sine theta all to the power of 3/2, just because we have a 1/2 here and a 1 here. And now, so as you can see from the graph of e to the anything, it never equals 0. So what you can write in your answer is that e to the 1/3 cos theta does not equal 0, as e to the 3rd cos theta is greater than 0 for all theta. And then you can basically just cross this out, and now we could solve this as a regular expression. So I'm going to take this to the other side, and I'm going to say 1/3 of sine theta all to the power of 3/2 is equal to 1/2 sine theta to the negative a half cos theta. Now I'm going to times both sides by sine to the half, just so I can cancel this term out here, and that will give me a third sine squared theta is equal to half cos theta. Now this is regular trigonometry, which you've done many times. We can use the identity sine squared theta plus cos squared theta equals 1, and we can basically do sine of 1 minus cos squared theta is equal to a half cos theta. We can rearrange, so we get a third minus a third cos squared theta is equal to a half cos theta. So we get 0 is equal to a third cos squared theta plus half cos theta. Just checking I've done everything right up to now yet. Minus a third, and then if we try factorize this somehow to get solutions for cos theta, what we can do is times everything by 3 and 2, so we get 2 cos squared theta plus 3 cos theta minus 2. Then in brackets we have 2 cos theta in this one and cos theta in this one, and we need to somehow make 3 in the middle, so we do plus 2 and minus 1, so we get cos theta is equal to a half, or cos theta is equal to negative 2. Now, using the graph of cos theta, sorry, that's the graph of sine theta. Let me just delete all of this. So from the graph of cos theta, we know that it's between 1 and negative 1, so cos theta is between 1 and negative 1, therefore cos theta equals minus 2 has no solutions. So we know that this is the correct answer and that theta is equal to pi over 3. Now I'm going to go back up to the top and I'm going to plug this in to find the maximum value of r. So r is equal to root sine pi over 3 times by e to the third cos of pi over 3. This gives you, so sine pi over 3 is root 3 over 2, so this goes root 3 over 2 times by e to the third times by a half, and that gives us our final answer of root 3 over 2 times by e to the 1/6 as in the question. So this might seem like a lot of working, and it is, that's why it's worth 7 marks, but really it's just applying trigonometry and maximization using differentiation in terms of polar curves. So that's why I'm saying it's not, the concepts aren't too difficult, but applying it to a polar curves question might be slightly more tricky, and that's why it's really important you cover these kind of questions. So I hope this video is helpful, and I'll see you in the next one. Bye.